so back to the storage. I went to school in the 1970s. It was very expensive. And so as cheap as I could make mistakes. Now I work at a university where it costs $50,000 a year to go to school for tuition and so it's very different. But back when I was going to school, it was very cheap. And so I had the luxury of not really listening to anybody else. So I just took classes and whatever I felt like taking classes. And eventually I got a degree, undergraduate degree in sociology, but I was in psychology and I was in art history, all kinds of things. But I was doing that as a preparation to go into architecture, which is what I always thought I would do. Unfortunately, I was wrong. But I stayed in architecture. I teach in an architecture school, and eventually I got a PhD in architecture by design. So it's a practice-based PhD, which some arts have as well, but in architecture it's quite rare. I had to go to Australia to get it. It took a really long time. But that, in part, that was because my own practice was rather strange. It wasn't like any other architects. So I wanted to share a couple of projects. One is has to do with aerospace. It's a project that I did with NASA Johnson Space Center and my students, and it's an exercise machine for microgravity. And then there's some projects that I was working on. I got interested in perception, and I started working on how one might extend the modalities that one can experience. I got some projects about magnetic fields. And then I have a kind of strange experiment with the vibration of steel plates, which might also be of interest. And I had some sound files. I'll play that at the end. In an effort to keep
yes, I'm sorry, but I left the cave in this way because I couldn't have you see?
Yep.
Yes,
no problem for me. Yep.
You're in the gauge.
All right. Okay, so I've been doing some talks, actually vary quite a bit, about redesigning human, and it is an idea that I have about the relationship between humans and technologies, and how technologies are very much altering what we understand ourselves to be. And technologies could open up what we consider to be humanity to design, not really in terms of genetic design. Maybe I should start with a story. I had a friend who invited many people to dinner. I was an architect, the architect, but also biologists, engineers, people in social science, artists, a group probably a lot like this. And at one point, the conversation got to it was a conversation that had a lot to do with emergent behavior and so on, but it got around to whether or not humans were evolving. And the biologists took control of the conversation and said, well, look, this is how it works, folks. There's no real isolated human populations anymore. And you need that in order to differentiate. And you have medicine and social programs that make it, that reduce the selection pressure on people, and so you're not going to get that kind of evolution anymore. And we think that we can start to do things by genetic engineering or other means, but it's not really very close to happening. And then once it happens, it's probably going to be subject to all kinds of social concerns and controls and regulations and things like that. So it's really, human evolution is finished for the time being. And I thought, well, that's kind of the response I would expect from a biologist. Right? So a biologist looks kind of at the organism and looks at morphology and says that's what the organism is. But from my perspective, the human or the organism of any kind and its environment are together. And the environment that we have here, the atmosphere that we have here, is produced by biology a long time ago. The plants that we have out here are precipitations of the atmosphere. Right? And so there's biology on top of biology, in which we're participating. The thing that's interesting about humans is that they're not very smart. And so they think they are. Most of them really think, and you always hear it, well, there's evolution, and top of the evolution is the human beings, and they're so cool, and they make stuff. It's true, there's lots of stuff. And we're now in the Anthropocene. We're in the era in which humanity is changing the Earth more quickly than anything else. And whether or not that's because we're so smart is a question, and we'll see what the future thinks of us. I think we won't. The future will see what they think of our intelligence. It might be that people aren't that smart. It might be actually that what they're doing is they change the environment and simplify it to make it easier for them. If you look at many texts, they'll say human beings, they're not very strong, they don't run very fast, they don't have good claws, they don't have sharp teeth. So what is it? Well, we fool around and change things. It's a little trick. But when we do that, there's a kind of residual effect. Stuff lays around in the environment, and the next people that come around, they have it a little bit easier. They've got a rock that's been shaved, or whatever the story is, all the caveman stories. But we change the environment over time. And we're at the point now where we've changed the environment enormously. If you want to do an experiment to find out how smart you really are, drop your cell phone in a cup of coffee, and see how many addresses you remember, how many phone numbers you remember. But you have the phone, it's here. And it works good. But much of what I can do and much of the effectiveness I have is due to these things. Due to the planes that bring me over here, due to the conversations that we might have over the next couple of days. I'll gain a lot from that. But it's due to the fact that the environment has been radically altered. So I told the biologist this, and I said, you have already admitted that you can't do very much. But, the architects, we change the environment. We do a terrible job most of the time. But we change the environment, and that's part of how people evolve. The culture, the environment has been crafted, and we don't even have to change the organism. Because it's defined by a relation. It's not defined by the morphology of the organism. And that relation is what I'm interested in as an architect. And so some of the projects I'll show have that as kind of the underlying situation. Thank you for the coffee. A lot of you drink this stuff, right? And I guess everybody knows how to make it, more or less. And one time a friend of mine came into my design studio and said, we want you to design a way to make coffee. And the students said, well, we know how to do that. We drink a lot of coffee. But he said, well, we're going to do this for astronauts on the International Space Station. So it was really interesting because all the things that the students thought they could do, like boil water and pour it through the ground, that doesn't work anymore. So there's no boiling and there's no pouring. So it was interesting to watch the students come to understand something about the nature of gravity and all the things that gravity does. And the best way to do that was to pull the rug out from underneath, take gravity away, and rethink everything without gravity. And that's a good way to understand exactly what that force is doing. So eventually the students, it's not at all that interesting, eventually the students come up with the fact that if you're going to do this on the space station, more or less you're going to microwave it. And more or less you're going to push the water through the ground. So most of the designs ended up to be something like this one had a cup as part of it. It kind of looks like Kind of looks like the cups that you used to have when you were a baby, you know. But, it all works fine. But that was the introduction to a series of problems that this particular man, David Fitz, came to introduce my design studio to. And over the period of about a decade, on 6 occasions, we did projects for the habitability and human factors group at NASA Johnson. And what they were asking us to do was to consider designing something that was a problem for them, and they thought they might benefit from having a bunch of design students just think about it and show them some possibilities and so on. So it was an interesting switch from having an environment which was, you know, pretty well engineered. I mean, they have 15,000 people at NASA Johnson, and they have a lot of facilities, and they're all working hard to make sure that we can put somebody in a strange environment and bring them back safely. And they spend a lot of time thinking about it. So it's strange when when they have something that hasn't been thought of before. So the first project they asked us to think about was to give astronauts a work surface. When you're floating around in space, of course, you can set something right here and more or less stays there, drifts around a little bit. But the astronauts wanted to have a work surface, and so the habitability and human factors people said, well, think about work surfaces, just come up with some ideas, and we'll take a look. And this particular, this is a student project, but this particular group of students came up with an idea for a lot of these small cells that would be able to aggregate together. And they worked with a mathematician who was very much interested in surface filling geometries. So this is very much like a pendulous tile, probably many of you know what pendulous tiles are. But what was great about this is the students said, well, that kind of fills the surface, but let's screw up the geometry so it overfills the surface. And when it overfills the surface, it pops up. And when it pops up, it starts to develop structural capacity. So that was kind of an interesting thing. But otherwise, these things, these little items would, well, there's another problem, which is that the things don't stay on surfaces, so they tend to float off. And one of the solutions that was found early on was to have airflow hold something against a surface. So they would have a return air duct, and they would put, let's say, a paper napkin there, and then they would put small parts there and hold it. So the students picked up on that and thought that they could hold things onto their little, they're kind of like pads, by using air. And that means that if the air comes in, it's got to exit. And when it exits, if the thing is sitting in space, it starts to move around. So they thought they could have these flocking pieces of furniture that would fly around the space station. NASA hated the idea. It was kind of cool. I mean, I've never seen flocking furniture before, so that was cool. Another group came up with these inflatable things, which are wearable, and which are like atoms that nucleate into some kind of strange molecule. But basically, what we understood, having worked with the astronauts and so on at NASA, was that what they were interested in was not to hold something up, not to keep something on the surface, but to make relationships between themselves and others that were structured. And that's what this furniture is doing here, kind of. It's actually getting in the way if we get rid of these tables. They were looking for social organization, and they were looking for cognitive organization. So they were, if they were working on something, they would like to put their work out here, like I do when I'm writing a paper. And this organization in space is absolutely the organization I need in order to do things. So these two functions, which are more or less buried, start to bubble up to the surface when you take gravity away. When you sort of remove that as the general excuse. So that was quite interesting. While we were up there, while we were thinking about the space station, understanding the space station situation, we started to understand also the physiological transformation that takes place when you're in microgravity, so bone density changes and things like that. But in the next year, they gave us another project, which was to figure out how people might live on the surface of Mars. They wrote a technical description how to get there, but they didn't really have an idea what it would be like to live there. And so the students thought, we had different groups working on different things, I won't show all of it, but one group of students thought about bringing all of the pieces together. And what was interesting was that it makes a lot of sense. It's very expensive to take something to another planet, as you might guess. Not on my debit card, thanks. But anyway, they thought if the things are there, bring them together and build a community out of the residue from several different missions. And what was interesting was that that's a great idea, but you have to have it first. Because if you don't incorporate a way to connect before you send it up there, you're not going to get one once you get up there. So they were very interested in that as a particular option. We also looked at things like how one might grow food and things like that on the surface of Mars. But these things were interesting because they started to alert us to problems of being in space. And these are interesting problems, but they're not the problems that we have here. One of the issues is that you're basically living in a tin can, and it's not a very big one. So the space inside the space station, it's about as wide as this table. And it's square. So it's about that high. And that's it. And it's a tube. And it goes down, and there's another tube connected to it, but it's kind of like continuous hallways. And if you're going to go to Mars, it's going to be even smaller. So there's a problem with being in confined spaces like that. Some of the apartments I had in New York City were that size. This guy, David Wolf, is a PhD in physiology and a medical doctor. And you can see he's kind of a big guy. And he was on Mir for 4 months. And each of the months he lost 11% of his muscle mass. He lost bone density. He had changes to his heart because it wasn't pumping against gravity. As a doctor, he knows exactly what's going on. He works real hard. He exercises a couple hours a day. He exercises so hard he breaks the exercise equipment. And they asked us to think about exercise in microgravity and what that might be. And so it was interesting. The body adjusts to microgravity, and then when it comes back to Earth, it's got to readjust. It's like it took them a year to do that for 4 months in space. So the adjustment's very radical. If you were, people say, well, your body deteriorates in space. Well, not actually. The body's just changing. It's not alerted to the fact that you want to come back. It just adapts to the conditions. And so, that was an interesting, for us, it was an interesting realization that what we think humans are like is because we're anchored by the similar conditions that we live in. And if we alter those conditions radically, then what we are like might be really quite different. That's a slide from another presentation. So these are the issues that we wanted to address. The sending somebody into space is so expensive that they keep people really, really busy all the time. And so the astronauts don't exercise very much because they're busy like you are. And some of you don't exercise, maybe, whatever. I don't. But so the doctors want them to exercise more. The mission specialists want them to get their work done, and they want to get their work done. They want to exercise because there's a conflict we can't get done. The confinement thing I just talked about, doing in a very, very small space, and then you need to do the exercise. So we thought, why can't we solve 3 of those problems all at the same time? In fact, the presence of one problem suggests the solution to another problem. So what we came up with was an exercise machine that was an interface to a virtual environment, where people could use it for training and for entertainment, and to experience larger spaces. They could experience running on a beach or something like that. It's very much like this interface that Jeffrey Shaw made. Jeffrey Shaw is an artist, he's an artist that created a bicycle interface to a virtual environment in the 80s. It happened to be quite a bit, about 10 years before ours. So this is really what it would be like. We had a problem that NASA is very concerned about any mass that has to be taken from Earth and go into space. So what we decided to do was to say, well, you have an astronaut, you have an exercise machine, you have a computer, you have a screen. All we're going to do is send up some code, put all those things together in a new way, and with the stuff you've already got on board, we can address this issue. So they're actually quite interesting. This is a machine that we made. It absolutely would not work in gravity, in microgravity, but it works in gravity. We did a presentation to people at NASA, but we also had a Biennale in Portugal that we had to present at. So we wanted to do both things in the same semester. And unfortunately, we had to split the budget in half. We had a small budget, and then we cut it in half. So it was quite slender. But what we did was build this sort of bicycle interface to a digital environment. And the technologies involved are fairly simple. We have inputs, just the velocity and direction, and we have some very simple outputs. Basically, they're tactile transducers of sound and a magnetoreological brake. That's a brake which is two discs that are rotating next to each other. In between is the fluid, and the fluid is, let's say, it's oil with iron filings in it. And you put a magnetic field on it, and the iron filings line up, the viscosity changes, and it's very difficult. You release the field, and it's very, very fluid, and so on. That's the kind of thing that basically was what the pedals are attached to. And so you could feel yourself going up a hill or down a hill or whatever. I mean, you could vary as much as you wanted the effort that's necessary to move forward. The technology was almost silly. It's just a variable resistor. It's kind of like a volume control. I'm sure you've all seen it. That one, the magnetoreological fluid devices inside here. This is simply a tiny motor, so it's acting as a generator. And then we have some tactile transducers made out of some broken speakers, which are easy to find on any college campus. And the students found a way to build these things on the internet somewhere. We built a couple of tactile transducers. So that's more or less what it's like. We have sound on either side, and one grabs onto the handles and rocks back and forth. When you lean over this way, you move in the virtual environment this way, and so on, and kind of forward and backward. This was done for about $2,500. The whole project for NASA and for Portugal was done for about $2,500. So most of the metal that you see there was used road signs that we found in the you can see the signs we found in the junkyard and so on. So it's basically made out of junk as much as possible. One of the students, we took the seat adjuster out of his Toyota, and we got the bicycle parts from a bicycle shop in Junkyard. So these are just simply some amplifiers and some linear power supply. And all these cables go back to a computer projector. So the setup was really quite simple, but very effective. The curve is quite difficult. Even people who make furniture usually try to design their own curve, and then after failing about 10 times, they go and get their grandmother's rocking chair and trace it. And that usually works very, very well. We couldn't quite do the rocking chair thing. That's not what we're doing here. It was very carefully crafted to be responsive in the middle and less responsive at the edges, so that when you lean over, you actually come to a part that's flat and it stops.
The way turned off. It's again.
go. So anyway, we tested it. It was a lot of fun. It seemed to work really well. When it was on exhibition in Portugal, there was a reporter that came to talk to me to cover the work. And she brought her boyfriend, who had a great time. He was pedaling away and so on and so forth, and he was so excited, and he rocked the thing up on these points. Like they were just about to tip over. Nobody had ever done that before. You think you know what's going to happen, you never have an idea what's going to happen. This guy was just about ready to flip the thing over. Absolutely amazing, but he was engaged. And, you know, the thing is, we were trying to create experiences for our astronauts. We didn't have very much money, but it doesn't matter because the experience doesn't come from the technology. The experience comes from the body. The body's working hard, the muscles are fatiguing, you're sweating, you stink, whatever. You're working, or you're like this guy, this woman's boyfriend, very excited, testing it out, running around and doing all kinds of things. So I think that was also a good point for us to understand. That's what it looks like. In Portugal, we had this planet that was shaped like a torus. So we were interested in giving somebody the experience of a planet, gravity, a planet shaped like a torus. So it's kind of strange. There are things you might be able to do that you don't actually get otherwise. Yeah. So anyway. So I was very much interested from this machine in how people perceive and the relationship between the body and the technology that we can have. And maybe it sounds spontaneous now. We think that
suspicion.
Yeah. Suspicion is not correct. Scientific suspicion. We often think this world is the one that we have, but in some cases, you know, there's evidence that it may be a fraction to the negative 35th, which is rather small. And you know, if you remember your chemistry classes, you remember that almost all these gases are always described the same way: tasteless, odorless, colorless, blah 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 blah. Right? So they're just here in the atmosphere. There's lots of stuff that we don't have access to. If you look at the sensitivity of different animals, most of us are up here. These look like they're better designed. They're a much more even distribution. Ours is kind of doesn't look optimal. But anyway, there are many other animals that have different kinds of eyes. Snakes have these infrared pits on either side that perhaps are like imaging, that help them to locate things in space. Fish have these organs that we believe might be for magnetic fields. And we have no idea what it is. It's like, okay, it's probably something. And you know, there are people who think that we have many different kinds of senses. This is one book that suggests, I don't know, there must be 13, 14, 15 different senses. And you know, I think there's a relatively recent philosophy which is thinking that things like mathematics and logic come from the kind of body we have. It's less maybe that mathematics is something out there that we discover, and more something that we understand based on our experience. So you know, there is a guy, Ian Stewart, who wrote a book called "Does God Play Dice?" It's an early book about the complexity of mathematics. And early on in the book, he says that mathematics may actually be more the structure of the mind than the structure of the world. And it changes the structure of the mind. And then, once the mind has been altered, we start to understand the world in a different way. I'm sure that's debatable. But there's also this guy, Rodney Brooks, who's an early robot guy, and he was quite critical of the way in which robots were being built in the, I believe, in the mid to late 80s. And he found a different approach. He said logic is something which is a new trick. Perception is something which is an old trick. Let's start with perception and let's start with bugs and build our way up. Which I thought was brilliant. Unfortunately, his next project was Cog, which was a humanoid thing. So it seems to be a desire to make more humans. We have like 11 billion. We don't even know what to do with them. We've got to fix them all. I don't know. But the idea that the standard model of perception, which is about information coming into the body, is still pretty strong. This is Brian Keeley in writing in 2002 is making this description about what constitutes a sense modality, and he said it's all about getting information into the brain, which I don't know. Now, I wouldn't argue that you don't have sense modalities. I just think it's a poor way to describe how it is that we interact with the world. And there's a lot of problems with it. There's a lot of discrepancy on what kinds of, how many and what kinds of senses we may have. My favorite is this one here, which is between 10 and 33. 21 of which are generally accepted. By who? Anybody who thinks there's 21 senses. But anyway, a lot of times senses are talked about in terms of modalities, which are an interesting analytic device. It's a decomposition, which really is about description and analysis, but it doesn't really help us put things back together again. But I think it starts off with Aristotle, and Aristotle said there are 5, so I have a seminar and I ask my students how many senses we have, and they always say 5. They never remember sense of humor, and none of them have common sense, so they're already off by 2. So there's got to be more. But part of the problem is that when you say something like vision, you seem like you're talking about something, but what you really want to talk about is color, or you want to talk about acuity, or you want to talk about motion detection. There are all these other things that are buried within this bigger kind of picture. Touch is the same way. Hearing is very much like that, which you probably are well aware of. There was an interesting, I read up on how we came to understand that bats echo their mates. Right? And that took until 1938. You'd think these big ears would have been kind of a clue. But actually it took a really, really long time. And we did experiments were done in Geneva in 1794 or something like that. That showed that if you block the ears of a bat, you can't catch its prey anymore. And the basic response from other scientists at the time was, well, if bats see with their ears, they must hear with their eyes. So that's a level of critical discourse which is interesting, but as a matter of fact, you hear with your eyes. I hear with my eyes for sure, in more than one way. But I hear with my eyes because my hearing's not very good. So I'm lip reading. I'm not combining sound and this. I'm hearing what people say. But more importantly, there's a recent study, which you may know, that shows that the eyes receive ultrasonic information. And it comes in through the orbs and rattles the brain, which stimulates the cochlea, and you're able to perceive higher than 20,000 hertz. And this is thought to not only be a factor in fidelity of sound, but may also have neurological problems and may develop tinnitus and things like that. Because anyway, there's a lot more to the sensory. And there's a lot of studies in the last couple of years about cross-modal perception, which is interesting. They all have the same base, more or less. Some of them are a little bit earlier, but mostly it's a 21st century problem where people are starting to look at the interaction between senses. And surprisingly, when you look at the interaction between senses, you find it. And if you don't look for it, you don't find it. That's kind of the way it works. If you think, if you're looking for something, you can get there. But there's some evidence that, quite a bit of evidence that the auditory cortex or the visual cortex is not where that stuff gets processed, but auditory information is in the visual cortex and visual information is in the auditory cortex. The motor cortex is far more important than we thought, and basically it more or less tells us that these kinds of labels are part of an older tradition, coming probably out of dissection, but coming from people who were interested in structure, and they looked at structure, and they found structure. And if you look at process, or you look at interaction between two senses, that's what you're going to get. Which I think is really, really interesting. Is in the bottom quote there. The results seem to be heavily dependent upon the paradigms used and so on. This guy, Randall Beer, is a researcher in dynamical systems theory for cognition, and I love this quote by him because I think it's worth all researchers understanding. The framework that you bring to the question determines the question that you ask, how you investigate it, what kind of evidence you do, how you do your analysis, the conclusions you make. Basically, you walk in a door with a framework, and it determines the answer. That's a really interesting thing. So many people are looking at perception as not being about information anymore, but about being a preparation for action, or actually being the result of action. And many people have talked about this. Vatarana says the mind is not in the head, the mind is in behavior. And these the long quotes by Varela, horses, closely associated with that on the thought. This is a very old work. This is not mine. This is a guy named Paul Makirita. He was a rehabilitation researcher. And in the 70s, late 60s and early 70s, he and a guy named Collins and a few other, but very few other people, were working on trying to give a sense of vision. So this is an old studio camera, a dental chair, and some captors that are on this guy's back. And he can read that word through the skin of his back, which is very cool. And the reason I like the work is because it throws all the other theories out in one kind of school. I love working with them. So it's like the slate is clean now. You have to think about something different because this should not work. And the other thing that happens is Akirita, when the technology gets a little bit smaller, which it was doing, in that time frame, still does to a certain extent, you can have this tactor device and start moving it around. And if I have it on my back one day and I put it on my forehead the next day, it still works. So the idea that there's information going through a nerve to a spot in the brain, that doesn't make any sense at all. I move it from here to here. There's other things that are very interesting about that work. In the previous slide, the machine was split right back, right through here. You can see a bank here and a bank there. That's because the spine is in the middle and it's not very sensitive. It can't actually reach you too much. But you don't have, you would like it, you like that. So, in any case, the image is not split in the middle. He doesn't see like 3 of the letters here, 3 of the letters here, like the blind spot that you have in your eye, because where the optic nerve comes out, there's no problem with that either. But there's a couple of things which are absolutely critical to this work. One is that if you took the latest Star Wars movie or whatever, and you played that video through the guy's on the guy's back, you would never see anything. He's got to move under his own will, and the correlation between that movement and the changes that come through the video camera is what seeing is. This is fundamental to perception. And so that's really what guides the movement, the ability to move these things around the body at different points. This is a tongue interface which works pretty effectively. It's a great electrochemical environment to work with. The amount of electricity you need is very, very small. The unfortunate thing is you got this thing hanging out of your mouth, which makes you look really weird. It's not very good socially, but yeah, it makes you look like a snake. I used one of these things. It was very, very strange. There's a group of philosophers, Charles Linné is one of them, who was trying to discover the least amount of information necessary to externalize the perception. So they used a photodetector and a vibrating pager motor. And as long as you can move in 3 dimensions, you're able to externalize the stimulus. In this case, they used a dark room and the photodetector. You get to move around freely, you can do it. So I thought, well, there's kind of a debate as to whether or not Baki Rita's machine is seen or not. It's not a particularly interesting debate. I don't think it's actually seen, but in fact, I thought, well, if Baki Rita can have, his subjects can have a new experience, like being able to read the word on the blackboard, I could give myself a new experience, and magnetic field might be the thing to do. So as far as I know, I don't perceive magnetic fields now. So, but it's a cheap sensor and a cheap guy, so we could do it. This one is an 8-axis automotive compass and parallax chip and so on, and it's got some vibrators and vibrating pager motors, cell phone motors in the belt. So this is one of the prototypes. You don't wear that in the airport. Not cool. I took this to Australia and tried it out down there, because down in this part of the world I have trouble with which way is north too. Everything's screwed up. Partly, I realized from that experience, partly that I most likely know about the orientation from light. So the light's coming from the wrong place now. But anyway, I had the opportunity to wear this through the city, and at one point I noticed that it didn't work very well anymore. And I was a little bit irritated with my grad student who just built it before I left, but it was really not reliable. But finally, the trains back to Central Melbourne showed up, and I got on the train, and I started to feel the magnetic fields and these big motors in the train. And those little Van Allen belt diagrams that they have, supposed to show you what the magnets is, not happening. These things are moving and swirling in there. It's really quite amazing to be enmeshed in these fields. And then I realized that when I was upset with my grad student, was because I was standing underneath the lines for the train, power lines for the train, and somewhere 5 kilometers away, the train was leaving the station and drew a lot of power through the lines, and this thing was reacting to that. So the problem wasn't with the device, the problem was with my understanding of what was going on. I thought this was for the Earth's magnetic field, but it's not. Of course, it doesn't know that, it's just responding. But it was really interesting to be able to move through environments and start understanding that there's lots of stuff going on that we don't have access to. When I'm using this device, I'm walking around so the action is locomotive, but you could also do something at a smaller scale. So since I'm an architect and I draw a lot, I figured I could make use of the skills that I have in drawing and move this probe over that complex magnetic field. All those little rare magnets understand density. And also worked on a glove. This one was initially starting off as a coil in the back of the hand, but eventually became a small solenoid with a cord boot in it. It's a sensor, and I could feel magnetic fields. I used to have a demo where I would plug in a coil to my machine to move it over the keyboard, and it's very active. So there's lots and lots of stuff going on, lots of noise, which you don't perceive. So, this is kind of the setup. You have something in the world which is in a logical, lawful, regular relationship to my movements. And when that happens, I can start to perceive that regularity and make sense of that regularity. So this idea of having a different mode, a different understanding of perception, which is about action and movement and things like that, it turns out that you can start making devices on that basis. And I believe that with some research, one could learn to understand any manufactured sensory technology and how to interface that to the body. So you could begin to perceive just about anything you can manufacture as a sensor for. So the human sensorium could be opened up to all kinds of things. That's kind of an interesting proposition. But some of you who might know Maturana and Varela's work on autopoiesis and cognition know that the organism is understood to be informationally closed. So I don't actually know what's going on outside myself, but I make these inferences. That makes it possible to cut that sensor off and supply some kind of data set that has a regular relationship to it, and potentially be able to directly perceive just about any kind of data that we might have. And I've been recently having conversations with people who have dramatically large data sets, difficult to analyze data sets, and most of the time they're trying to visualize, which means making a three-dimensional representation of two dimensions, or maybe getting the thing to move with animation or something. We're just leaving out a lot of our ability to perceive, and I think that is also a very interesting proposition. This is a picture of a recent building in my university, which is called MPAC, Experimental Media and Performing Arts Center. And the big wooden thing inside the glass cage is a concert hall. It's quite a nice facility. I've seen some great concerts there. It's got a 15 decibel floor, so it's very, very nice. And there's many other facilities there. One of the things that they have is a 360-degree screen, which goes in one of their experimental theaters as well. It's now toured. And it's also the home for a center called the Center for Cognition, Communication, and Culture, which I'm one of the founders of. And it's housed in this building, one of the theaters, quite beautiful structure. And this is a project that we have going on, being built while I'm here, so I don't have to participate in it. But it's basically like a cave. It's a 360 surround screen, and it's got 192 channels of sound. So there's three rings of 64 channels, which is going to be quite spectacular. And in my university, my colleague who's the head of this is an acoustician, architectural acoustician, a musicologist, and psycho-acoustician, and an electrical engineer. And so we're building this very interesting device, which we hope will be out by the end of the year. And the idea here is that many of these caves are based on the kind of pilot model. You know, a lot of this technology grows out of military kinds of endeavors, and this human-machine interface idea was never very social. And one of the things that we wanted to do here is create an environment in which people can work together and move that away from the single user. And in order to do that, we're using this space. We used wave-field synthesis to create good acoustic properties to any spot in the room. And the tracking will be both by camera and by microphone. So we're actually trying to use similar methods for how humans track, which is to use sound and sight at the same time. But the idea here is to be able to put people in sight, sound, and tactile conditions that will allow them to do a bunch of collaboration. So we're hopefully going to have an opportunity to do some fun work. So this is the last project. When I was studying perception, I was interested in the edges, and this is kind of an architectural problem in a way. I'm approaching it like an architect. When I'm designing this wall, this part of the wall is not interested. That's a problem. And the door is a problem. The top is a problem. The bottom is a problem. So the general field is whatever, but the edges are always kind of cool, and they tell you a lot more about the system than the middle does. So when I was interested in perception, I wanted to find out about perception that was below 20,000 hertz or 20 hertz. So I said, well, I need to build a subwoofer, so maybe something about 6 feet in diameter. So I went to my colleagues in architectural acoustics and said, I'm going to build a speaker that's 6 feet in diameter, and they started laughing. They were right. But basically, as part of that, I was using a tactile transducer or a voice coil and a lot of different kinds of materials. And I did lots of experiments. I eventually did build something that was a tuned resonator, which worked out pretty well. And what I found out from that is that I thought that I wasn't supposed to hear this stuff, but those deep frequencies, you perceive them even if you don't hear them. And it's kind of like what I was talking about with the eyes. Above 20,000 hertz, it counts. It's important, even though the ears aren't sensitive, because you don't hear with your ears. You hear with the whole body. But I didn't know that then. This is a complete failure, because what I did is I put the voice coil on a piece of steel, and it's far from being responsive. And one of the problems is that I wanted to build a speaker that didn't make any sound. There's not a lot of information on that. It's not a big market for that. So nobody knows what to do. So I had to just directly experiment. When I used this stuff on steel, I got these really interesting tones that came up. So I started working with that. And one of the things I noticed was that there was some very interesting behaviors that came out of it. So what I was doing was trying to understand what this thing would be like at different frequencies. I wanted to make these low frequencies. And when I did that, I would put a frequency in it at a particular amplitude, and I would let it run for a while and listen to it. So I have one. I think it's getting kind of late, so I'm not sure I should play this first one.
No, please.
Yeah? It's
Yes.
okay?
Yes.
All right, so I'll just play this, and hopefully...
I don't know if the loudspeaker is going to be strong enough. It's very low.
It's not super low, no.
Okay, let's try
Let's
this.
try it.
Maybe it's sort of, because maybe it's muscle.
Well, it starts off real soft. Hopefully. That's kind of what that looks like. So it starts off, this is, very, very low amplitude. It kind of changes in here and picks up. This part will probably mask. But there's these distinct phases that are happening. And even within that, some other phases, which are quite interesting. So this is where you have 38 hertz at a very low amplitude for 7.5 minutes, and this structure develops, which is pretty fascinating. So I started to do experiments along those lines, and a lot of times I got quite complicated behaviors. I work mostly with things I buy on eBay and things like that. So I had signal generators, old amplifiers and things like that. And one day I was listening to the sound. I used to. This one was one of the shortest ones. There's many that take a lot longer to develop, which I spared you. I work in my research space and turn on the frequency and amplitude and let it run. And I would develop these interesting structures, but one time it just stopped. And I figured my equipment broke. I went over to the plate and I could see it moving like that. It just wasn't making sense. And then it started again. So you can see in the middle this kind of zone where it goes into a completely different behavior, and then it comes back out of it again. Probably this is 3 or 4 seconds later. Which is what it used to be. And that sounds kind of there was another time when I had behavior, maybe it was something like that, and I thought, this is really interesting. I need to record this and show it to my colleagues. And so I turned the thing off, and I went over there and I damped the plate and thought, well, I can start over. And what happened was really interesting. It didn't start over. As I showed you, it goes through these different phases. It starts off and gets more and more. At the end is kind of like sound effects, thunder, shaking. I turn it off and I damage the plate. Instead of starting over, it just goes back to the thunder thing. So that's what you see here. And this is me damping the plate, talking about it, and turning it back on. And it goes, there's something where it remembers where it was, and goes back to that phase, which I thought was very cool. It kind of sounds like this. Should play. Didn't play. But we can play that later. One time when I was out of the country, as I am now and again, the steam pipe in my research space broke. It had a wooden floor, maple floor before that. It was an old classroom. And the floor buckled, so they took all my stuff out and they put a concrete floor in. And they didn't really put things back. And after that, I never quite got the same behavior from the place. You know, I didn't disassemble things, and so there was no records kept or whatever, where things were. But I'm not sure exactly why. But I'm never able to get that kind of neat phasing stuff that I was getting before. I think it may have to do with the way in which the apparatus was coupled to the floor. And the concrete doesn't do that anymore. I I had a sense when something would happen. If you're listening to this thing vibrating, you could get somehow a sense that it would change its phase. It was very, very subtle shifts. But I like that. I like to hear these. And so, but I found that a lot of times when I started to leave the room, it seemed like it was going to shift. And I would go back and I would sit down and wait for it to shift, and it never would. Then I'd get bored and I'd get up and I'd move towards the door, and it would seem like it was going to shift. And I realized finally that I was just moving in a different place in the sound field. And it sounds different near the door. So when I got near the door, I thought something would happen because it transformed somehow. But in any case, so I think it does really have to do with location. It seems like the fact that I was expecting that the thing would change because of the shift was because I thought that the speaker made sound when I listened to it. And I didn't really realize that the sound exists in space. When I move around in space, I'm moving around through the sound. And I should have expected it to be different, but I still had this other perception in my mind. When I got the concrete floor, I got this kind of behavior. It would just start shaking dramatically. It didn't go through the phases. And, you know, it would do that. Like this is an hour. And I had never really listened to that noise. It's not pleasant. Never really listened to it for more than an hour. But I was recording it one day, and I was the administrator. I was associate dean of the school, so something came up. I had to leave. I left the recording going on. I didn't get back for 9 hours. This is what I found when I got back. I'd like to play it for you, but I won't. Okay. But I could see it. I could see on the plot that something really interesting happened. It went into this kind of phase for 5 hours, and after that, it changed again. And so, the last thing I want to do is just play some excerpts from what this is like and what a few of these things are like. I think that will close. So I'll do that. And I sped it up 3 times. absolutely a valid question. I can answer. I'm not actually interested in some ways. I'm interested in everything. But, another question is, why didn't I expect it? Why did I think that if I have a piece of metal and I put 38 hertz in it and don't change the amplitude, that it's going to be giving me 38 hertz back? And many people expect that. And I think what it has to do with is that people still have this kind of what I identify as a mid-20th century appreciation for information data. And that the material is secondary, passive, in response to the data. But the material is not anywhere near that. And I think that that's what we could hear, is that the material and the environment together are producing this, what I think is sometimes beautiful, but very complicated, very interesting behavior out of a simple stimulus. So part of that has to do with, I think before I was talking about going to the door, part of that has to do with conceptually, where do I bound the system? What do I think this, when I describe this, how far out does my description go? The phenomena goes out as far as the phenomena goes out. And when the description doesn't quite go out as far as the phenomena does, then the behavior doesn't match what the framework says should have. And maybe that's, for me, the most important thing to draw out of this is not the descriptive, but the epistemic dimensions of these kinds of